Hi, I'm Satvik and now I'm going to explain about expanders. Expanders. This is a special sort of graph that has remarkable properties and many applications in real world. It is a graph that is very hard to disconnect because every set of vertices in G is joined to many edges of its complement graph. Uh, Expanders have spawned research in pure and applied mathematics with various applications in the fields of complexity theory and design of networking systems, which we'll see later in this video. Now we'll see the mathematical definition of expanders. Let X be a graph with vertex set V and cardinality n, and let us define Y, which is a subset of vertices V, such that the cardinality of Y is less than or equal to half times V, which is equal to n by 2, and let us define dou Y, which is boundary of Y, that is it has a set of vertices which are not in V, but the vertices in dou of Y may be neighbors of the vertices in V. Then if dou of Y is at least epsilon times the cardinality of Y, then the graph X is said to be an epsilon expander. The largest epsilon for which X is an epsilon expander will be denoted by epsilon of X. Being an epsilon expander for large E means that X is strongly connected graph. Now, before going into more details of expander graphs, we'll see what the term regular graph is. Let X be a graph on set V of vertices and A be an adjacency matrix on the vertices, which is usually 1 or 0 depending on whether an edge is there or not, but it may be more than 1 because we allow multiple edges and loops. Now the graph X is k regular if the degree of every vertex is k, that is every vertex has equal number of neighbors, which is k. These are the examples of k regular graphs, and this is a 1 regular graph, this is a 2 regular graph, and so on. Now in most applications, what one wants is to find regular graphs with large n and fixed k and fixed epsilon with as large value as possible. Family of k regular graphs will be called a family of expanders or an expanding family if all of them are epsilon expanders for the same epsilon, which is more than 0 and less than 1. Now we'll see the existence of expanders. The first person who proved the existence of expanders was Pinxer. He proved that if n is large and d is more than or equal to 3, then almost every d regular graph with vertices number n is an expander. That is, he proved that if there is a constant c which is positive, such that for every fixed d value, the proportion of d regular graphs with vertices n that are not expanders tends to 0 as the value of n grows to infinity. Now this proof was proved using the probabilistic method. Now if a d regular graph is chosen at random, then the expected number of edges leaving a set S is this, which is at least half times the value of d into cardinality of S. And then by using some standard tail estimates, we can prove that the probability of number of edges leaving a set S is significantly different from the expected value, and it is as small as 0. Now we'll see different notions of expanders. The first one is an edge expansion, which is similar to the definition we have seen earlier. And an edge expansion constant h of g, which is also called Cheeger constant, is defined as dou of s by s, where dou of s is a pair of vertices u and v, where u belongs to s and v belongs to the rest of the graph excluding s. Now in this equation, the minimum is over all non-empty sets s of at most n by 2 vertices, and dou of s is a edge boundary of s. Now we'll see a different notion, vertex expansion, which is almost similar to the first one. The vertex number h out of G of a graph is defined as dou out of s by s, where dou out is a outer boundary of s, which has a set of vertices which are not included in V with at least one neighbor in S. Now we'll see some dependence of expanders on spectral theorems and eigenvalues. We have seen that to be a C expander, it involves that all subsets of vertices have to be checked, which is a very long task as the number of subsets are really huge, and indeed this problem turns out to be a NP C problem. Now we shall now describe a closely related property that can be checked in polynomial time and which is in some way more natural. Now the third notion, which is a spectral expansion. Given a graph G, its adjacency matrix A, which is same as defined before. This matrix is real and symmetric and therefore has n real eigenvalues lambda 1, lambda 2, so on to lambda n, which mean name in such a way that lambda 1 is greater than or equal to lambda 2 and so on to lambda n, which has been proved by spectral theorem. Moreover, the eigenvectors and their values are orthogonal. Now since we have used the notations, we need to prove that A acts as a linear map. Take a function f which is defined on vertices of G, then AF is a function whose value at u is the sum of f of v over all neighbors v of u. From this we see that if G is a deregular graph and f is a function that is 1 at all vertices, then AF is a function that is d at every vertex. This implies a constant function is an eigenvector of A with an eigenvalue d. This is the largest possible eigenvalue lambda 1, and that if the graph is strictly connected, then the second largest value lambda 2 will be strictly less than d. The difference between d and lambda 2 is called spectral gap of G, and it measures the spectral expansion of graph G. Now we'll look into Cheever inequalities. When G is deregular, there exists a relationship between h of G and the spectral graph of G, and the relation is this: half times d minus lambda 2 is less than or equal to h of G, which is less than or equal to 2d into square root of d minus lambda 2. From this it follows that an infinite family of deregular graphs is a family of expanders if and only if there is some constant A which is positive, such that the spectral gaps are at least A for all graphs in the family. Now we'll see the possible strategies that are followed in constructing a family of expander graphs. The first strategy is sort of group theoretic and algebraic, and the second one uses combinatorics, and the third one, which is the latest one, uses the zigzag graph product. There are many wide applications of expanders in real life world, and one of them is in networking. In application to networking systems, one wishes to devise a network configuration for which the edge expansion constant, which is h of g, which we have seen earlier here, is high, at least bounded away from 0, even when the number of systems is large. For example, take a ring network of n which is more than two systems, which is sort of this kind, where each node represents a system, and define V of g as a set of vertices and E of g as a set of edge pairs between adjacent nodes. Now take A to be a group of floor function of n by 2 of these systems in a chain. Let A be 1, 2, 3, so on till floor function of n by 2. Then dou of A will be the pair of vertices that are not included in A but have some neighbors in A. So they will be n by 2 and n by 2 plus 1 and n comma 1. Since now the edge expansion constant is dou A by A, and since the cardinality of dou A is 2, we see that this is 2 times the value of floor function of n by 2. And now we see that as n tends to infinity, this value tends to 0, which means that the edge expansion constant or Cheeger's constant will also tend to 0 for large values of n. Now take a situation where two non-adjacent systems are broken. Then say the top one and the bottom one, then the system will become highly disconnected and the performance will be reduced greatly. So the value of expansion parameter should be kept high to avoid such problems. This is one of the application of expanders, and there are many other applications in real world. Thank you.
Hi, this is Sandeep. We shall now discuss about the greatest mathematician the world has ever known, Johann Carl Friedrich Gauss, who was a German mathematician who contributed significantly to many fields like number theory, algebra, differential geometry, mechanics, electrostatics, astronomy. I believe this list won't be ending soon. So moving forward, there is very interesting story about his birth date. His mother was illiterate and never recorded the date of his birth. She remembered only that he was born on Wednesday, 88 days before the Feast of Ascension, which occurs 39 days before Easter. Then Gauss tried to solve this puzzle about his birth date in the context of finding the date of Easter. He derived methods to compute the date in both past and future years. He then calculated his own birth date and believed it was 30th April 1777, a truly remarkable feat. By the way, he was born in Brunswick. From the very beginning, Gauss showed an unusual talent for numbers. He could calculate before he learned to speak. When he was 8, studying in elementary school, he figured out how to add up the numbers from 1 to 100 as a pairs of 50 pairs, each pair summing up to 101. In 1788, Gauss began his education at the gymnasium, where he learned his High German and Latin. After receiving a stipend from the Duke of Brunswick, he entered Brunswick Collegium Carolinum in 1792. At the academy, he independently discovered Bode's law, binomial theorem, arithmetic geometric mean, as well as law of quadratic reciprocity and prime number theorem. These were his works just at the age of 16. He studied for a doctorate at the age of 49 for 3 years from 1795. Later in 1796, he constructed a regular 17 gone by a regular compass and showed that a regular polygon can be constructed by compass and straight edge only if the number of sides is the product of distinct Fermat primes and the power of 2. That year was the most productive for both Gauss and number theory. While studying at Göttingen, Gauss's outpouring of his new ideas changed mathematics forever. He completed his book Discussions Arithmeticae in 1798 at the age of 21, but it was published in 1801. It is regarded as one of the most influential mathematics books ever written, which laid foundation to modern number theory. He left University of Göttingen in 1798 without a diploma. Gauss was remarkable for popularizing the practice of standard notation A plus IB for complex numbers. He also interpreted complex numbers graphically. In the area of probability and statistics, he introduced what is now known as a Gaussian distribution, the Gaussian function curve. He showed how probability could be represented as a bell shaped which peaks around the mean or expected value and quickly falls towards 0 plus or minus infinity. His second publication was Discovering of Asteroid Series. However, he did not reveal his idea of calculation. He claimed to have done to the logarithmic calculations in his mind. Then he worked for many years as an astronomer and published a major work on computation of orbits. In 1810, he was honored with the Lalande Prize with the French Academy of Sciences in the recognition of his contributions to astronomy. Gauss also wrote on cartography, the theory of map projections. For his studies of angle preserving maps, he was awarded the prize of Danish Academy of Sciences in 1823. He also discovered the possibility of non-Euclidean geometries but never published it. This discovery was a major shift in mathematics, as it freed mathematicians from the mistaken concept that Euclidean axioms were the only way to make geometry consistent. He formulated Gauss's law, which related the distribution of electric charge to resulting electric field. The law was used to derive Coulomb's law and vice versa. He showed that its magnetic field can be defined by using purely mechanical dimensions, mass, length and time. He introduced Gaussian surface, an arbitrary closed surface in 3D space, which the flux of gravitational field, electric field and magnetic field can be calculated. Thus he contributed to geophysics. He invented the heliotrope, an instrument that uses a mirror to reflect sunlight over great distances with the purpose of marking positions on land survey. These are used until late 1980s when GPS replaces this technology of heliotrope. He is referred to as the greatest mathematician since antiquity and is considered as one of the history's most influential mathematicians. From 1850 onwards, Gauss's work was again nearly all of a practical nature. Although he did approve Riemann's doctoral thesis and heard his probationary lecture, his last known scientific exchange was with Galen about a modified Foucault pendulum in 1854. The Carl Friedrich Gauss Prize for Applications of Mathematics, named in his honor for outstanding mathematical contributions that have found significant applications outside of mathematics. Finally, he was considered as the last man who knew of all mathematics. Thank you.
Hi, I am Rahul Bandari. Now I am going to explain about Nullstellensatz theorem. It is an important theorem which relates different branches of algebra. Like it relates linear algebra with geometrical algebra. Now let us see what is this theorem and its proof. Define the statement of this theorem. Let us take a d-sized tuple z equals to z1 to z2 so on up to zd. Now let f1, f2 so on up to fn are the collection of polynomials in d-sized tuple. Then there exists g1, g2 so on up to gn, which are also polynomials of d-sized tuple such that it satisfies the following relation. so on up to fn into fn of z into gn of z equals to 1. Then there exists no z which satisfies all fi of z for all I equals to 1 to n. We can see this as if z satisfies fi of z, then fi of z equals to 0 for all I equals to 1 to n. Then this implies LHS equals to 0 but RHS equals to 1, which is false. So there should not be any z which satisfies above relation. Now this is called as effective Nullstellensatz theorem. Now there is an alternate theorem which is a converse of the effective Nullstellensatz theorem, which is called as weak Nullstellensatz theorem. Which states that there is no d tuple of z such that fi of for all I equals to 1 to n is satisfied. Then the relation f1 of z into g1 of z so on up to fn of z to gn of z equals to 1 is satisfied. Such that gi of z is also a polynomial of d tuple z. This is a converse of the Nullstellensatz theorem, which is also called as weak Nullstellensatz theorem. Going to the proof part of this theorem, effective Nullstellensatz theorem can be proved with the help of weak Nullstellensatz theorem. Now, weak Nullstellensatz theorem can be necessary condition, but it is also a sufficient condition for the proof of this theorem. Now, let us assume h is another polynomial in d-sized complex tuple. Then r is a variable such that h power r can be written as follows: h power r equals to f of f1 into g1 plus f2 into g2 so on up to fn into gn. Now g1, g2 so on up to gn are some collection of polynomials in d-sized tuple. Now it follows that if h of z equals to 0 whenever f of I z equal z f of z equals to 0 for all I equals to 1 to n. Now we can see that the theorem statement which was given above can be seen through. So this proof, that is h of z equals to 0 for all f of I equals to 0 where I equals to 1 to n, then there must exist g of I of z for all I equals to 1 to n such that h of r equals to f of g1, f2, g2, so on up to fn gn. Thus, the above theorem is proved. Hence proved.
Hi, my name is Naveen and I'm going to explain about the application of expanders. Application of expanders. What are error correcting codes? Error correcting codes is one of the application of expanders. Basically, an error correcting code is an algorithm for expressing a sequence of numbers such that any errors which are introduced can be detected and corrected based on the remaining numbers. The detection of these errors is much simpler than correcting these errors. These error codes are essential in computing and all sorts of communication. The question which arises is that how can we possibly not only detect an error but also correct it as well? A fundamental application of coding theory is the detection and correction of errors. Parity error. Parity error checking was the first error detection code and it is still used today. It has the advantage of being simple to understand and simple to implement. It can also be extended to more advanced error detection and correction codes. To consider how parity works, we consider an 8-bit item of data. Suppose this is an 8-bit item of data 00100 0010010. If you imagine that this was stored in a less than secure form, then if a single bit was changed from a 0 to a 1 or vice versa, you would never know. So, if instead of storing these 8 bits, we store 9 bits, with the ninth, the parity bit, set to make the total number of ones odd or even, then you can see that a single bit change is detectable. So if you select odd parity, then the 9 bits are 1, 0, 0, 1, 0, 0, 1, 0. That is, the parity bit is a 1. And if any single bit changes, then the parity changes from odd to even, and you know there has been a bit error. Parity checking detects an error in a single bit but misses any errors that flip two bits, because after any even number of bit changes, the parity still remains the same. The parity error checking is used when there is a fairly small probability of a single bit change, and hence a smaller probability of two bits being changed. Having distance. When you first meet parity error detection, it all seems very simple, but it seems like a one-off rather than a general principle. For example, do you extend it to detect a 2-bit or 3-bit error? In fact, parity checking is the simplest case of a very general principle, but you have to think about it in a slightly different way to see this. When a bit is changed at random by noise, you think of the data word as being moved a small distance away from its true location. A single bit changes moves it a tiny amount. A 2-bit change moves it further, and so on. The further bits that are changed, the further away the data word is from its original true location. A simple measure of this distance between two words is to count the number of bits that they differ by. This was called as the Hamming distance. This has been named after R.W. Hamming, who did much of the early work into error detection and correction. For example, say there are two data words 011 and 110, which are 2 units apart because they differ in two places, the first 0 bit and the last bit. What has Hamming distance got to do with parity check? If you take a valid data word which has a parity bit associated with it and change a single bit, then you have a data word which is one Hamming unit of distance away from the original. So every valid code has an invalid code word away 1 unit from it. Working of an ECC for data storage. ECC is the error correcting code. When a unit data or a word is stored in RAM or a peripheral storage device, A code that describes the bit sequence in the word is calculated and stored along with the unit of data. Say if I read 64-bit word, an extra 7 bits are needed to store this code. So when the unit of data is requested for reading, a code for the stored and about to be read word is again calculated using the original algorithm. The newly generated code is compared with the code generated when the word was stored. If the code matches, the data is free of errors and is sent. If the codes do not match, the missing or erroneous bits are determined through the code comparison, and the bit or bits that are not corrected are supplied or corrected. No attempt is made to correct the data that is still in storage. So eventually it will be overlaid by new data, and assuming the errors were transient, the incorrect bits will go away eventually. Any error that recurs at the same place in storage after the system has been turned off and on again indicate a permanent hardware error, and a message is sent to a log or to a system administrator indicating the location with the recurrent errors. At the 64-bit word level, parity checking and ECC require the same number of extra bits. In general, ECC increases the reliability of any computing or telecommunication systems without adding much cost. An example: one of the most fundamental problems in communication is noise. Assume that a person A has a message of k bits which he or she would like to deliver to another person B through some communication channel. The problem is that the channel might interfere in the way, and thus the message that the person B is supposed to be receiving from person A might be different than the one that person A has originally sent. The problem over here is that the communication is through a noisy channel. In this problem, person A and person B can communicate over a noisy channel that might change the proportion P of the bits sent through it. So how can a person A send a message of K bits to a person B without the data being manipulated? The solution to this problem was suggested by Shannon. In the solution to this problem, Shannon suggested building a dictionary C, which is a set of strings 0, 1, such that the number of elements in C is equal to 2 to the power k. Every k bits message is encoded by a code word in C, and it is being transmitted. The person B receives n bits and finds the closest code word in C in terms of Hamming distance, and determines the k bits associated with it. If the minimal distance between two words in C is greater than 2p, and where p is a proportion, it is guaranteed that the k bits that person B will find is exactly the bits person A encoded. Therefore, the problem of communicating over noisy channel is reduced to the problem of finding a good dictionary. So, the person has to just find a good dictionary to reduce the problem of the noise. Uh, the previous slide has been represented in a mathematical form. Here, the rate and distance of a dictionary. Let C is a set of the strings 0 to 1 be a dictionary. The rate of the dictionary is defined as R. R is the rate, which is equal to the log of the number of elements in C by n, while the distance of the code is written over here, where dh is a Hamming distance. There are few more applications of expanders, namely random walk on expanders. Taking an L-step random walk in an expander is in a way similar to choosing L vertices at random. Another one is a cryptography. Again, using random walks and constructive expanders, one can transform any regular weak one-way function into a strong one while preserving security. The next one is complexity, amplification of success probability of randomized algorithms. And the last one is coding theory, asymptotically good error correcting codes based on expanders. Thank you.